Hello everyone, welcome back to the channel. The goal of today's video is to help you crush your final exam. I'll walk you through a set of practice problems that cover the major topics you're likely to see. And I'll share strategies for tackling box problems, mechanisms, and synthesis questions with confidence. Now let's dive in. The first question asks us to provide the reagents that could convert the carboxylic acid into an amide. The strategy to solving this problem will be to apply retrosynthesis. You will have to try to split this molecule into smaller fragments, and to decide where to split the molecule from, you need to compare the starting material with your product. Notice that this part of the product is similar to the starting material. Now, this gives me an idea of where to split this molecule from. I will have to split this molecule from here. And the two fragments that will result from that will be this and this. So I can convert this to my starting material. And for the other fragment, all I have to do is to make that into an amine. The next thing would then be, how can I make an amide? To make an amide, we need to react an acid chloride with an amine. Since what we have is carboxylic acid, I will need to convert this carboxylic acid into an acid chloride. To do that, treat the carboxylic acid with thionyl chloride, which will convert the carboxylic acid into an acid chloride. And if you treat the acid chloride with amine using pyridine, then you would make the amide. Now the answer to this problem will be, I will need to write two reagents. One is thionyl chloride, two aniline and pyridine. So these are the reagents that will transform the carboxylic acid into product. Next question. This question is asking us for the product that will form when a carboxylic acid reacts with a strong base. Now, when a carboxylic acid reacts with a strong base, deprotonation will occur in that the strong base will grow up one of the acidic proton on the carboxylic acid, and this will form a salt. So our product is going to be this carboxylic anion, and the counter ion will be attracted to this negatively charged oxygen. The conjugate acid would also form, and these are the products. For this question, since this reaction is taking place under light condition, we would have radical mechanism. And radical mechanism is in three steps. We have initiation step, propagation step, and termination step. The products are usually formed in the propagation step. Now, in the initiation step, the bond between the two bromine atoms would break under light condition. We call this homolytic cleavage. And when that bond breaks, one electron goes to this bromine atom, the other electron will go to this other bromine atom, and we would have the formation of bromine radicals. In the propagation step, the radical will abstract a proton from the substrate and convert that substrate into a radical. The way this happens is that the bond between carbon and hydrogen will break. One electron will go to this carbon, and the other electron will be used by the proton to form a bond with the bromine radical. The substrate is converted into a radical, and now we have hydrogen bromide. This radical will then react with more bromine reactants and convert that bromine into a radical, and in the process, the product will be formed. However, we should also realize that this allylic radical can be resonance stabilized, meaning this can undergo resonance. Now the pi bond can break, one electron goes to this carbon, the other electron will be used to form a bond with this radical. And we have another allylic radical. Now these two radicals could react with neutral bromine and then form the product. That means we'll have two types of major products. So this allylic radical can react with neutral bromine. Here the bond breaks, one electron goes to this bromine atom, the other electron is used by this other bromine atom to form bond with the radical. So this is going to be one of our products. Now the other bromine, the other allylic radical can also react with a neutral bromine. So here, the bond between the two bromine atoms will break. One electron goes to this bromine, and the other electron is used by this bromine to form a bond with this allylic radical. And we would have the other product. So the major products are formed in the propagation step. Now in the termination step, the radicals will start combining together to quench the reaction when all the reactants have been completely exhausted. So for my answer, I will write these two products. So I'm going to have this as a major product. Then I will have this as another major product. This question asks us to convert this primary alcohol to this secondary alcohol. For this type of question, we need to apply retrosynthesis. Now compare the starting material with the product. You'll notice that this part of the product is the same as the starting material. The new addition is this methyl group. So the question then will be, how can I split this product into simpler fragments? If I cut this molecule through this bond, I will split the molecule into two components, the alcohol, primary alcohol, and methyl group. So the question will be, how can I attach a methyl group to a carbon that is bonded to an oxygen? One strategy to do that will be to use Grignard reaction, and Grignard reagents usually will react with carbonyl compound. Since our starting material is not a carbonyl compound, I will have to convert this to a carbonyl compound. Do that, I will oxidize the primary alcohol using PCC, which is pyridinium fluorochromate. So PCC will oxidize the primary alcohol to an aldehyde. Next, I will need to treat this aldehyde with Grignard reagent. The Grignard reagent is a strong nucleophile. And it's a strong nucleophile because the bond between carbon and magnesium is severely polarized due to the huge electronegativity difference between carbon and magnesium. With carbon being very electronegative, it can pull electrons from the bond, breaks the bond, use those excess electrons to then attack the carbonyl carbon of the aldehyde, and this will push the pi electron towards this oxygen, and we would have these tetrahedral intermediates. Now CH3 group is now attached to the carbon. The next thing will be to protonate the negatively charged oxygen using an aqueous acid. And this will eventually form a product, a secondary alcohol. So the answer to this question will be 1, I have PCC. 2, I need to use Grignard reagents. And of course, we will do acid workup. This question asks us to provide the product of this reaction. Now, since we're reacting this compound with this set of reagents, we know that this is an EAS reaction. And this set of reagents will generate the bromonium ion as the electrophile. The bromonium ion will then be attached to the ring. But the question then is, which of these two rings are we going to attach the electrophile to? Now, to determine the ring where we're going to attach the electrophile to, we need to focus on the atom that is directly attached to the ring. So the first atom that is directly attached to ring A is this oxygen. Does that oxygen have a lone pair? If it does, then it's most likely an electron donating group. And since oxygen have a lone pair, it means it can donate electron into the ring. So this will be considered an electron donating group. On ring B, the atom directly attached to that ring is a carbon, which doesn't have an electron, which doesn't have any lone pairs. And that carbon is doubly bonded to an oxygen, and the carbonyl group is an electron withdrawing group. On the EAS chart, an electron donating group is higher than electron withdrawing group, and the higher group usually will activate the ring. So this means that the bromonium ion is going to be attached to ring A. For what part of ring A are we going to attach the bromonium ion to? The electron donating groups are generally orthopara directors, while electron withdrawing groups are meta directors. So the ortho position from the oxygen on ring A is this or this. So we can attach the bromine to either of those positions. And we will have another bromine attached at the para position. So my product eventually will be this. I will have two products. One where bromine is attached at the ortho position, and another where bromine is attached at the para position. To provide the product of this reaction, we need to know that when a carbonyl compound like a ketone or aldehyde reacts with an amine under acidic condition, the product form is going to be an amine. And to draw the product of this reaction, start first by drawing the ketone. Next, replace the oxygen of the ketone with the nitrogen from the amine, and the alkyl group on the amine will remain. That's going to be the amine, which will be the product of this reaction. To provide the product of this reaction, we need to identify what type of reaction is taking place here. Now, since we have two carbonyl group, we have two carbonyl compounds reacting with each other under basic conditions. This reaction is an Aldol condensation. And in an Aldol condensation, the base is going to deprotonate the alpha carbon of ketone. Here, the ketone is our nucleophile, and formaldehyde will be the electrophile. So the base will deprotonate the alpha carbon. This bond is going to break, and then a negative charge will be formed on this carbon. I like to use the minor resonance structure whenever I'm doing reactions, but if I'm solving a mechanism problem, I'll form the major enolate. So in this case, we're going to have the minor enolate. So this enolate is our nucleophile. The enolate is going to attack this carbonyl carbon of the electrophile, and we would have this intermediate. The negatively charged oxygen is going to pull an electron from the conjugate acid that is formed in situ, and will form an alcohol. Now this is beta hydroxyketone. And that's the product of Aldol condensation. Next question. In this reaction, we are reacting an alpha-beta unsaturated ketone with a strong nucleophile. Now, a strong nucleophile like Grignard reagent prefers to attack the carbonyl carbon, and this will usually give a 1,2 addition reaction. Carbon, being highly more electronegative than magnesium, will pull the electrons from the bond breaks off, and then the carbon 1 uses that electron to attack the carbonyl carbon, and this would push the pi electron towards the oxygen. Now, the ethyl group from the Grignard reagent will form a bond with the carbonyl carbon through carbon 1. In step 2, the negatively charged oxygen will get protonated and then forms the product. We're asked to provide the starting materials that will form this Diels-Alder product. In a Diels-Alder reaction, we know that a dienophile will react with a diene under heat conditions to form the product. Now, dienophile is usually an alkane, while the diene usually will have 2 double bonds in it. Applying retrosynthetic analysis, I will need to split the product into 2 fragments. The question then is, where can I split this product? Now, I need to identify the dienophile component in the product. Dienophile usually will have electron withdrawing group, and we can see these electron withdrawing groups here. I would have to split this molecule here. If I do that, two fragments that will generate from that would be this. And the other fragment is this. Now I need to convert these fragments into the respective reactants. Dienophile usually is an alkene, so all I have to do is to make this into a double bond. The diene usually will have two bonds. I will place those bonds here and here. And these will be the starting materials that will make the Diels-Alder product. Next question. This question asks us to predict the starting material that will make this product. Now, since the reaction is Wittig reaction, there are two reactants that are usually combined to form the product in a Wittig reaction. These are a carbonyl compound, such as a ketone or an aldehyde, and yellide reagent. So when a yellide reagent reacts with a ketone, the product usually will be an alkane. Start by drawing the ketone, then replace the oxygen with the negatively charged carbon of the yellide, and that carbon is joined to the alkyl group. And this is the product. So all you have to do is to place this part of the yellide reagent on the ketone by replacing the oxygen of the ketone with the carbon of the yellide. And that carbon is usually the one that has the negative charge. Okay, based on this, let's now solve this problem. The question will be, how can I split this molecule into two fragments that make sense? This is where to do that. I have two fragments. I need to make one of them into the yellide and the other into the ketone or aldehyde. So we have this fragment. I can make this fragment into the yellide. To do that, I will need to place a negative charge on this carbon where it joins to the other fragment. The other fragment will be the other reactant. I'll just make that into a carbonyl compound. So these will be the two starting material that are needed to make the product. I can also make the top fragment into the carbonyl compound and the bottom fragment into the yellide reagent. And to do that, I can make this into the carbonyl compound. And that means that the yellide is going to be this. So this carbon will be made the negatively charged carbon. And the negatively charged carbon is usually bonded to pH3 plus. So either of these two reactants will suffice. I could choose these two as the answer, or the answer could equally be these two. Next question. We're asked to provide the starting materials that are required to make this product. And we're told this reaction is Claisen condensation. Again, apply retrosynthesis. To do that, I need to find a way to split this molecule into smaller fragments. In a Claisen condensation, two esters will react. One is going to be made the nucleophile and the other one the electrophile. In the product, the nucleophile usually retains its ester components. So that means this part is going to be my nucleophile, and the electrophile usually loses its ester component in the product. So that means this part is going to be my electrophile. Now that I've identified the nucleophile and electrophile components in the product, I will need to then identify the alpha carbon. And I know that the nucleophile usually forms a bond with the carbonyl carbon of the electrophile through its alpha carbon. This gives me an idea of where to split this molecule. So I have to split this compound here, with this being my electrophile and this other part being my nucleophile. Now I will draw those two fragments in these boxes. So my nucleophile will be this. My electrophile is going to be this. So I need to make the electrophile fragment into a meaningful reactant. All I have to do is to give it an ester. Usually, I will use the same ester that we have attached in the nucleophile. Next question. This question asks us to provide the starting materials that are needed to make this product, the alcohol. Since we're told that this reaction is a Grignard reaction, well, in a Grignard reaction, the Grignard reagents usually will react with a carbonyl compound to form an alcohol. So I will need to apply retrosynthesis, and to do that, I want to find a way to split this molecule. All I have to do is to identify the oxygen and see which carbon the oxygen is joined to. Now that carbon will be a carbonyl compound that the Grignard react with. So I will need to split this molecule here. So my Grignard reagent will be this. And I will attach magnesium to this carbon that is originally joined to the carbon with the oxygen. And my carbonyl compound will be this. So that means I need to make this a benzaldehyde. Another way to do this would be, we can also split this molecule here. If we split this molecule here, this is going to be the Grignard component. And this other component will be the carbonyl compound. So that means my Grignard will be this. My carbonyl compound will be this. We're asked to provide the mechanism for this reaction. So let's start with the first part. If you react a diene with a dienophile under heat conditions, you form this product. But the mechanism is such that, first of all, we know that This is an electron withdrawing group. The electron withdrawing group is going to pull electrons away from this carbon, making this carbon electron deficient. So the pi bond from the diene will attack this carbon, and that's going to push the pi electron to attack this other carbon, which will push this pi electron to form a bond here. So the product is going to be a 6-membered ring. For this other mechanism, hydrolysis mechanism, the strong nucleophile is going to attack the carbonyl carbon and thereby push the pi electron towards the oxygen. We would have this tetrahedral intermediate, and the OH group is now attached to the carbon. Since there is a leaving group attached to the carbon, the carbonyl group will reform and then kicks out the leaving group. So we're going to have this, and the leaving group is here. Of course, the counter ion will be attracted to this. The counter ion is always attracted to the negatively to wherever there is a negative charge. Of course, this can also function as a strong base, which can deprotonate the carboxylic acid. However, since we have water in the reaction, the water will protonate the product back. We're asked to provide a mechanism showing how the benzene will be converted to a nitrobenzene. Now, this is an EAS reaction. So there are two parts to drawing the mechanism of this reaction. The first part will be to generate your electrophile, and the second part will be the reaction of the electrophile with the benzene. So the nitric acid is reacting with sulfuric acid. So this oxygen is going to pull off this proton from the sulfuric acid, and we would have this. So we're going to have this oxonium ion here. And of course, the conjugate base is also formed. The lone pair on the oxygen is going to collapse, forming the double bond between the oxygen and nitrogen, and water molecule will be kicked out. Here, let's use the equilibrium arrow. So when this happens, we'll have nitronium ion. We'll have water and, of course, the conjugate base. Now that we've generated the electrophile, we can now perform the second part of the mechanism, which is the EAS reaction. I'll start by drawing out benzene ring. And I'll make sure to draw out hydrogen on the benzene ring. The carbon where the hydrogen is attached to is where I would attach the electrophile to. And the carbocation will be on the adjacent carbon. So essentially what happens is that this pi bond will swing out and attack the positively charged nitrogen and then forms a bond with it. So the pi bond will break, and I will attach the nitrogen to the same carbon where the hydrogen is attached to. Now, carbocation will be on the adjacent carbon. This can undergo series of resonance, but I'm not going to draw the resonance structures. So water molecule would then serve as a base and then grabs this proton. The bond between hydrogen and carbon breaks, reform a double bond here. Nitrogen should have a positive charge. And this will be the mechanism. Next question. We're asked to draw the mechanism for this reaction. Now, when drawing mechanism, we need to notice the changes that happens, the subtle changes that happens here. Notice that methoxy group replaces the OH in the product. So that means we're going to have to attach the nucleophile and eject the leaving group. So this principle should guide us when we're doing the mechanism of this reaction. However, we know that the OH group is a terrible leaving group. So that has to be converted to a good leaving group first. Also recognize that this reaction is taking place under acidic conditions. And whenever you're performing a reaction under acidic conditions, the first step is always protonation, the carbonyl oxygen. So the carbonyl oxygen grabs this proton and will form a protonated carbonyl group. Conjugate base is also formed. Now we can do nucleophilic attack. So the nucleophile can attack this carbonyl carbon, and I'll push the pi electron towards the oxygen. Since oxygen now have 3 bonds, it will gain a positive charge. Recall that this is a bad leaving group. So we need to make it into an excellent leaving group. To do that, we have to do proton transfer. So we're transferring this proton from here to this oxygen. And to do that, the oxygen is going to grab the proton. The bond between oxygen and hydrogen breaks. The excess electron goes on to neutralize the positive charge on the oxygen. Now we have an oxonium ion, and we have a methoxy group here. So the lone pair of the oxygen of the hydroxy group collapses to form a double bond, thereby kicking out water molecule. We need to get rid of the positive charge on the oxygen. To do that, we can use the conjugate base that was formed earlier on to remove the proton. And the catalyst is regenerated. So this would be the mechanism for this reaction. This question asks us to show the mechanism for this reaction. Now, since my product is an alpha-beta unsaturated ketone, and I'm starting with a ketone, now this tells me that I'm going to have aldol condensation and dehydration. I know this is dehydration because of the double bond that is formed here. So to start drawing this mechanism, I need to figure out what the starting materials will be. Right? In an aldol condensation, two ketones or two aldehydes or an aldehyde and a ketone will react under basic conditions to form the aldol product. It could also react under acidic condition, but in this case, what we have is a basic condition. So what are my starting materials going to be? One, I know I have this ketone. So what is the other carbonyl compound that will react with this ketone? To determine that, I will need to cleave this molecule here. So this part is what I have already. The other part will be this. So all I need to do is to make that into a carbonyl compound. So that means it's the same thing as the starting material. So that means two of these acetone will react under basic condition to form the product, which is then subjected to dehydration. One of these is going to be the nucleophile, and the other one will be made the electrophile. The nucleophile, which is usually an enolate in this case, since this reaction is taking place under basic conditions, it will go through the formation of an enolate. So I'll need to generate the enolate, and to do that, I will react my ketone, the nucleophile, with the base. So the base will deprotonate the alpha carbon. Double bond is formed between the alpha carbon and the carbonyl carbon, and that will push the pi electron towards the oxygen. So I will have my enolate, which is also my nucleophile. Of course, the counter ion will be attracted to the enolate, and water is formed. My enolate nucleophile will now react with the electrophile. To show the mechanism, the carbonyl group will reform, and I will push this pi electron to attack the carbonyl carbon of the electrophile, which will then push the pi electron towards the oxygen. So a bond is formed between the alpha carbon of the nucleophile and the carbonyl carbon of the electrophile. And that carbonyl carbon of the electrophile has two methyl groups and an oxygen, which will become negative charge. Now, this tetrahedral intermediate, of course, will attract the counter ion. The next thing would then be to protonate that oxygen using water that is generated after the first step. So this oxygen will pull off this proton and would form a beta hydroxyketone. The conjugate base of the acid is formed, and again, the counter ion will be attracted to this conjugate base. So this is the aldol product. The next question would then be, this is the alpha and this is the beta carbon. How can we go from this to the alpha beta unsaturated ketone? So under basic conditions, the base is going to pull off, the base will deprotonate the alpha carbon, and will form an enolate. Counter ion is attracted to the enolate. Now, this negatively charged oxygen will reform the carbonyl group, which will then push the pi electron towards to form a double bond between these two carbons and eventually kick off the leaving group. And that will lead to the formation of the product and this conjugate base. Again, the counter ion will be attracted to the conjugate base. So this will be the mechanism for this reaction. Now let's do some synthesis problem. Provide a reasonable synthesis to show how this primary alcohol will be converted to this tertiary alcohol. Applying retrosynthetic analysis, one of the things we want to do is to find out the difference between a starting material and the product. Notice that this part of the product is the same as the starting material. Now we have two other group we have two alkyl groups that are attached to the carbon that is attached to the OH group. So applying retrosynthesis, I will need to split this molecule into simpler components. And the simpler components will be this. And then we have two alkyl groups, a methyl group and an ethyl group. We know that to attach alkyl groups to a carbon that is bonded to an oxygen atom, generally we need to use Grignard reagent. And Grignard usually react with a carbonyl compound. So that means I need to make these alkyl groups into Grignard reagents. Add magnesium bromide to this carbon and magnesium bromide to the methyl group. So those will be the other starting materials that will be reacting with this alcohol to form the product. Now let's begin our synthesis. The first step will be to convert the primary alcohol into a carbonyl compound. I will need to use a mild oxidizing agent, preferably PCC, pyridinium chlorochromate. So this will convert the alcohol to an aldehyde. Next, I will then react this with, I could start with any of these Grignard reagents. Let's start with the methyl group. Usually, whenever we do reaction with Grignard, we will do an acid workup step. So the methyl group will be attached to the carbonyl carbon of the aldehyde. And then that will push the negative charge towards the oxygen, which will eventually pull off a proton from the acid to form an alcohol. So when aldehyde reacts with a Grignard reagent, an alcohol is formed and an alkyl group is attached to the carbonyl carbon of the aldehyde. Next, we need to attach the ethyl group. However, we will need to convert this secondary alcohol into a carbonyl compound. To do that, again, I will use PCC, or I could use bromic acid, which is a strong oxidant in this case. Whichever one that we use is fine, since the secondary alcohol can only be oxidized once. So this is going to form a ketone. I can now react this ketone with the other Grignard reagent. Since we have ethyl group here, there should be two carbons on the Grignard reagent. always do acid walk-up step whenever we do a reaction with Grignard. And this will be the synthesis that shows how we can convert the primary alcohol into this tertiary alcohol. Next question. This question asks us to show how we can convert this starting material into this product. However, we're told to only use reagents that can add 2 carbons or less. As usual, we need to apply retrosynthesis. Try to split this product into 2 simpler molecules. To do this, I will need to split this compound here, since this part is similar to my starting material. So that's a good place to split the molecule. And since we're told to only use reagent that can add 2 carbons or less, this one has 3 carbons. So I need to also split that part. I can split this here. So the fragment will be this and this. And we have an ethyl group. To attach an ethyl group to a carbonyl carbon, we generally will use Grignard reagents. Now let's get started. We need to convert this into Grignard by reacting it with magnesium. So react that with magnesium metal, we would form a Grignard reagent. We can now react the Grignard reagent with this carbonyl compound. So if we react it with formaldehyde, now the alkyl group will be attached to the carbonyl carbon of the formaldehyde, and this is going to form alcohol. Again, there should always be 2 steps. One is the step involving the reaction of the formaldehyde with the Grignard reagent, and the second step will be the acid walk-up step. We need to convert this to a carbonyl compound and then react it with the next reagent. So I will use PCC, which will convert the primary alcohol into the aldehyde. Next, I will then react this aldehyde with this Grignard reagent. Of course, I will do an acid walk-up step in step 2. The ethyl group will be attached to this carbonyl carbon. And the carbonyl oxygen will form alcohol eventually. To convert this to the eventual product, I will need to oxidize that secondary alcohol. And I can use PCC, or I could use any other strong oxidant. So PCC is a mild oxidant. I like using this a lot. So this converts this to a ketone. And that will be the synthesis to this problem. This question asks us to propose a reasonable synthesis to show how we can transform the starting material, benzene, into this product. Now, the difference between the starting material and the product are these groups that are installed on the benzene ring. And all of these 3 groups can be installed using EAS, Electrophilic Aromatic Substitution Reaction. Now, what matters is the order in which we attach or install this substituent is extremely important. So we need to identify what type of directors we have. So the chloro group is an auto-para director. NH2 is an auto-para director. And the propyl group is also an auto-para director. However, these groups are meta position from one another. So that makes it difficult. Now, what to do would be to attach a meta director first, and that would direct the other groups to the meta positions. So what we can do would be to start by installing a nitro group to the benzene ring. So to do that, we'll react benzene with nitric acid and sulfuric acid. This would attach the nitro group to the benzene ring. Next, I can try to install this propyl group. To do that, I can do Friedecraft acylation using this reagent and this catalyst. The product from here will be such that the acyl group will be attached at the meta position from the nitro group. I'm not going to convert these to the alkyl group just yet, and that's because I need to attach the chloro group, and I need a meta director that can do that. And since this is an electron withdrawing group, it is a meta director. So now I can go ahead and install the chloro group. Let's convert the acid group first. I need to treat that with zinc mercury amalgam in HCl. And the carbonyl group will be reduced to an alkyl group. Lastly, we can now I can reduce the nitro group to NH2 using ion in HCl. Next question. Notice that a starting material is a 1,3-dicarbonyl compound, while a product is a ketone. The difference between a starting material and the product is that we have two ethyl groups are attached at this alpha position of the starting material. So we know a technique or a strategy to remove the ester group is to do hydrolysis and decarboxylation. Now, to attach alkyl groups at the alpha position of the 1,3-dicarbonyl compound, we need to do alkylation. And usually we will need a base to deprotonate the alpha carbon of the starting material. Since we have two alkyl groups, we're going to do alkylation twice. So the first step, we'll use a base. I want to use a base that matches the ester components of the reactant. So the base deactivates the alpha carbon, or it deprotonates the alpha carbon, and then the alpha carbon can now attack this electrophilic carbon of the alkyl halide and kick out the bromine group via SN2 mechanism. So the product will be such that ethyl group is attached at this alpha position. Next, we need to attach the second ethyl group. So we're going to repeat this process twice, use this base, sodium methoxide, and then we're going to use this alkyl halide. Again, the base will deprotonate this alpha carbon, and that alpha carbon is going to make a bond with this electrophilic carbon of the alkyl halide and kick out the bromo group. Now we have two ethyl groups attached to that alpha carbon. To remove the ester components, we will do hydrolysis. We could do the hydrolysis under basic conditions or acidic conditions. And that will convert the ester into a carboxylic acid. To remove the carboxylic acid group, we need to perform decarboxylation. Usually we'll use an aqueous acid and heat. That will give us the product. The next question asks us to identify which molecules are aromatic, anti-aromatic, and non-aromatic. To solve this problem, recall the rules of aromaticity. 1, there must be a ring in the molecule, and all the atoms in the ring must be sp or sp2 hybridized. Secondly, the molecule has to be flat. If a molecule doesn't satisfy these two conditions, then it is non-aromatic. But if it satisfies these two conditions, then we have to then determine whether it's going to be aromatic or anti-aromatic. So to solve this problem, first of all, let us identify the total pi electrons. And to calculate the total pi electrons, we need to determine the pi electrons from the pi bond. So let's call this pi electrons. Then we also need to determine the electrons from the lone pair. And then that will give us an idea of the total pi electrons. Now, to determine if the molecule is aromatic or not, we'll divide total pi electrons by 2. If it's odd number, we'll have aromatic molecule. If it's even number, then we'll have anti-aromatic molecule. Let's start with the first molecule. So in this molecule, we have 3 pi bonds, which means we have 3 times 2, which is equal to 6 pi electrons from the pi bond. And then we have 1 lone pair. That lone pair is part of the pi system, so we're going to count it. And it's part of the pi system because it can do resonance. That's one easy way to tell. So we have 2 electrons from the lone pair. The total electrons here, the total pi electrons will be 8, 6 plus 2. If you divide this by 2, you will have 4. Since 4 is an even number, this molecule will be anti-aromatic. For the next molecule, the total pi bonds here is 1. So that means total pi electrons from the pi bond is 2. We have 2 lone pairs on the oxygen. However, only one of the lone pairs is part of the pi system because only one can do resonance at a time. So we will only count just one of the lone pairs. And one lone pair has 2 electrons. So total electrons from the pi bond and the lone pair is 4. If you divide 4 by 2, you will have 2. 2 is an even number. Therefore, this molecule is anti-aromatic. For the next molecule, there is a ring, and all the atoms in this ring are all sp2 hybridized. Also, for the previous molecules, All these atoms are sp2 hybridized. So total pi electrons from the pi bond is 6. We have no lone pair, so lone pair is 0. Total pi electrons will be 6. 6 divided by 2 is 3. 3 is an odd number, therefore this molecule is aromatic. On the next one, there is a ring, and all these atoms are sp2 hybridized. So we'll also assume that this molecule is flat. So since this molecule satisfies rules 1 and 2 of aromaticity, we'll go on to determine whether it's aromatic or anti-aromatic. Total pi bond is 3, so pi electrons from the pi bond will be 6. The nitrogen has one lone pair. However, that lone pair is not part of the pi system. So we're not going to count that lone pair. Total pi electrons in this molecule will be 6. Divide 6 by 2, we'll have 3. Since 3 is an odd number, we can conclude that this molecule is aromatic. For this molecule, is there a ring? Yes. Are all atoms in the ring sp2 hybridized? No. The nitrogen is sp3. Therefore, this molecule is non-aromatic. For the next molecule, is there a ring? Yes. Are all atoms in the ring sp2 hybridized? No, because this carbon is definitely not sp2. It's actually sp3. Therefore, this molecule is not aromatic. Which of these molecules is more basic? To determine a stronger base, you need to look at the availability of the lone pair on the nitrogen atoms. So which of them can donate more electron density into the ring? This nitrogen can donate all of its lone pair or electron density into the ring. However, for the other molecule, we have an electron withdrawing group that is attached to that nitrogen. So that electron withdrawing group will pull electrons away from the nitrogen, thereby reducing the amount of electron density that is going into the ring. Since the first molecule have more electron going into the ring, it will be the more basic molecule. Which is more acidic? First of all, form the conjugate base of the acid. Now, whichever acid has the most stable conjugate base will be the stronger acid. If you form the conjugate base of these molecules, all you have to do is to pull off the proton in the molecules. The conjugate base for this molecule will be this. For this other molecule, the conjugate base will be this. So of these conjugate bases, which of them is most stable? The most stable is the one where the negative charge is better stabilized. And since we have it's an OH group. Since we have electron withdrawing group attached to the ring, the electron withdrawing group will help pull the electron density away from the oxygen towards itself, thereby stabilizing the negative charge a lot better. Now, for this molecule here, the OH group is a strong electron donating group. So that means the oxygen will be donating electron density into the ring, thereby destabilizing the negative charge here. So the most acidic compound is going to be this acid. And this is the least acidic compound because the conjugate base of that acid is highly unstable. Which of these will give the faster EAS reaction? In an EAS reaction, where S is the substituent, which could be electron donating group or electron withdrawing group. So if you react that with an electrophile, what happens essentially is that, so we're going to break the pi bond, and then we'll attach the electrophile on the same carbon that has the hydrogen, and carbocation will be on the adjacent carbon. The positive charge on carbon simply means that carbon is electron deficient. It needs electron. So if you have an electron donating group that can donate electron onto the ring, now it will stabilize the ring and the reaction will proceed faster. However, if you have an electron withdrawing group, now the electron withdrawing group will pull away electrons from the ring, thereby destabilizing the positively charged ring. Okay, and that will make the reaction to be very, very slow. In other words, electron donating group speeds up reaction, whereas electron withdrawing group slows down EAS reaction. So of these two molecules, this is an electron donating group. One way to easily tell is look at the atom that is directly attached to the ring and ask yourself the question, does it have a lone pair? And yes, it does. So that's an electron donating group. That's one way to identify an electron donating group. On the contrary, the nitro group is a powerful electron withdrawing group. Therefore, the molecule that will give the faster EAS reaction is going to be the aniline. So this is where I will stop for today. I hope I've been able to equip you with skills and strategies on how to solve problems on your final exam.